Good morning, champs. Let's learn how to balance chemical reactors. So here you see a reactor where we have a molar flow rate of the species A at the inlet, which is Fa0. Within the reactor we have the reaction where A reacts to P, and leaving our reactor we have the molar flow rate of the species A, Fa, as well as P, Fp. So let's start off by doing a species balance for the species A. So species balance for species A. So within our reactor, we're going to have a change of the species A with respect to time. So let me write that down so you can take notes. With respect to time. Within reactor. So this is going to be equal to the molar flow rate of the species A at the inlet, denominated by Fa0, minus the molar flow rate of the species A at the outlet, which is Fa. So let me write that down for you. Fa0, inlet flow of species A, outlet flow of species A, plus the reaction rate of the species A times the volume of our reactor, which is VR. So VR is the volume of the reactor, Ri Ra is going to be the reaction rate. So the general species balance for a random species I can be determined as following. So the change of the species I with respect to time in a reactor is going to be the molar flow rate of the species I at the inlet, Fa0, minus the molar flow rate of the species I at the outlet, plus the reaction rate of the species I times the volume of the reactor. So, given that the molar flow rate of the species I is equal to the concentration of the species I times the volumetric flow rate. So this is the volumetric flow rate. So the general species balance can be written as the change of the species I with respect to time being equal. So if we factor out the volumetric flow rate, we can say that it's V times, in parentheses, the concentration of the species I at the inlet minus the concentration of the species I at the outlet, which is Ci, plus the reaction rate of the species I times the volume of the reactor. So with the molar amount of the species I being equal to the concentration of the species I times the volume of our reactor, and if we derive it with respect to time, so dNi with respect to time is going to be equal, if we insert for Ni the above mentioned formula, so Ci VR with respect to time. So let's refresh our memory from high school mathematics. So if we have a function which consists of a product, let's say u and v, and we derive it, we can use the product rule, v times u derived plus u times v derived. So in this case, ci is going to be u and vr is going to be v. And this would be equal to v, which is vr, times u derived. So u is ci, so we derive it, dci with respect to time. So this is v and this is u derived, plus u, which is ci, times v derived, so dvr with respect to time. So ci is u and this is v derived. So the change of the reactor volume with respect to time is going to be 0, because our reactor volume is going to stay the same independently of the time. So we can say that the reactor volume is not a function of time. Hence, this expression is going to be equal to 0. So this we can insert into here, and we can say that Vr times the change of the concentration of the species I with respect to time is going to be equal to the volumetric flow rate V times the concentration of the species I at the inlet minus the concentration of the species I at the outlet plus the reaction rate Ri times the volume of our reactor. So for our general balances we can use this expression as well as this expression which we just derived. So let's take a closer look into the forms we can operate our reactors. So one form of the operation would be the batch process. So in the batch process, our reaction mass is going to be in the reactor, and during operation there is no inlet nor outlet flow. So if we take a closer look into our general balance for a species I, so for the general balance we consider the inlet and outlet flow, but for a batch reactor these are going to be non-existent, hence both of them are going to be 0. So we can say that the change of species I with respect to time is going to be equal the reaction rate of the species I times Vr. So if we transfer it to the reactor we have shown here, we have a species A which reacts to the species P. We can say that the change of the species A with respect to time is going to be equal to the reaction rate of the species A times the volume Vr. And if we take a look into the other form of our general balance and we transfer it for the species A, so for the batch reactor we do not have a volumetric flow, so this is going to be 0, and we will end up with the volume of the reactor times the change of the concentration of species I with respect to time is going to be equal to the reaction rate of the species I times the volume of the reactor, and these two terms will cancel out. So for a batch reactor the change of the concentration of the species I with respect to time is going to be the reaction rate of the species I. So for this particular case we can say that the change of the concentration of the species A with respect to time is going to be the reaction rate of the species A. Let's take a closer look at the semi-batch reactor. So on the left you will see a reactor where we have a species A and B reacting to P, and we are inserting the species B during the process. So for semi-batch reactor one or more species are already in the reactor at the start of the operation. So in this case, our species A is already in the reactor. And one or more species is being added into the reactor during operation. So here it would be our species B, which is being added to our reactor during the process. And for each species we have no outlet flow during the operation. So let's take a closer look at the general species balance for a species I. So for a semi-batch, this equation will depend on the species we're taking a closer look at. So first of all, for both of the species we do not have an outlet flow. So our outlet flow Fi is going to be 0 for A and B in this case. However, for our inlet flow Fi0, this will depend on the species we're taking a closer look at. So Fa0 is 0 because our species A is not being added, it is already in the reactor. However, for species B, we are adding it during our process. So Fb0 is not 0. So for the species balance of the species A, so dNA dt, this would be equal to the reaction rate A times the volume of the reactor. However, for the species B, so dNB divided dt, this would be equal to the molar flow rate of the species B at the inlet, which is Fb0, plus the reaction rate of the species B times the volume of the reactor. So let's take a closer look into the other expression. So as I stated before, there's no outlet flow, so the volumetric flow rate times Ci is going to be 0. This is going to be true for A and B. And the product of the volumetric flow rate and the concentration at the inlet, which is Fi0, so the volumetric flow rate times the concentration of the species A at the inlet, Ci0, which is equal to the molar flow rate at the inlet, is going to be equal to 0. And the volumetric flow rate times the concentration of the species B at the inlet, which is the molar flow rate Fb0, and this is not 0, which we discussed before. So for our species A, the reactor volume times the change of the concentration of the species A with respect to time is going to be equal to the reaction rate of the species A times the volume of the reactor. So these two cancel out and we end up with the same expression as the batch reactor. However, for the species B, so this is Cv divided dt, this would be equal to the volumetric flow rate times the concentration of species B at the inlet plus the reaction rate of the species B times the reactor volume, and if we divide it with Vr, we end up with the change of the concentration of the species B with respect to time, and this is equal, well, the volumetric flow rate divided the reactor volume is equal to 1 divided the mean residence time. For this you could use tau. I have seen the term Tm for other textbooks, but here we will just stick with tau. So this is going to be equal to 1 divided the mean residence time times the concentration of the species B at the inlet plus the reaction rate of species B So now let's take a closer look into the CSTR, which is the continuous stirred tank reactor. And we'll take a closer look into the balance for species A. So for a CSTR we have a steady state, meaning that the change of time is going to be equal to 0. So if we transfer this to our general species balance, so there's not gonna be a change of the species I 2 times, so this is going to be 0 because we have steady state. So if we transfer this for a species A, we can say that 0 is going to be equal to the inlet molar flow rate FA0 minus the molar flow rate at the outlet FA plus the reaction rate of the species A times the reactor volume. And if we transfer it to the other expression, so here the change of the concentration with respect to time is going to be 0 because we have a steady state, and this will result in 0 being equal to the volumetric flow rate times, in parentheses, the concentration Ca0 minus Ca plus the reaction rate of the species A times the volume of our reactor.